Cool. So my name is Bryony, and I'm a fourth-year PhD student in Scotland. I work in the Criticat PhD program in chemistry. I'm shared between two universities, the University of St Andrews, which you can see a beautiful picture of the beach there. That's where I originally started my PhD, and I'm currently working at the University of Edinburgh, so I'm co-supervised. My pronouns are they, them. I'm also pretty cool with she, her, but you know, they, them is like the preferred ones for me. So a little bit about me and what's this talk about. So all about me, who am I, why am I here, what am I doing, which I think is a question that many of us ask every day. Introduction to what is photocatalysis, what can we use it for. A little bit more about things like climate change, which my PhD relates to quite strongly. I think a lot of science-based PhDs do nowadays. We're kind of approaching climate change from many different scientific angles. What are my photocatalysts made of? How do they work? Some further extremely niche applications of my kinds of photocatalyst, what lies ahead with that, and as promised, lots of memes, which I hope will live up to the expectations. Yeah, so to begin with, I'll just whiz through a quick introduction to myself. I did my master's in chemistry at the University of Durham, which, as you can see here, is very pretty. It's got a nice little cathedral. Here's me graduating in the cathedral. So I did a research-based master's degree, so that means I did an entire year placement in the lab of Anne-Marie O'Donoghue, who is absolutely top chemist, love her. We did a project that was focused on making stable organic radical systems. So a radical is a kind of organic molecule that has an unpaired electron. And this means that it's really, really reactive because electrons like to travel in pairs. So basically, these radicals are so reactive that we normally can't isolate them. They're normally like an intermediate in another chemical reaction. But my entire master's thesis was all about isolating some radicals that we could actually stabilize, and they were so stable we could isolate them as a powder and crystallize them, and then do all kinds of cool stuff with them in terms of using them as pressure sensors, and they're also quite conductive of electricity. So if you're really keen to read up on some very niche chemistry that was recently published in Nature Communications, you can annoy me on Twitter for the link if you want to. And then I loved research so much, I went on and started my PhD in a slightly tangential area to that, which was the Photocatalysis PhD program. So I started working in the lab of Professor Eli Zeisman-Coleman in St Andrews. This is the research group now down here. Believe it or not, when I first started my PhD, I think there were about 6 or 7 of us in the group, and it just keeps growing. There's just more and more people, which is really cool. It's a lovely bunch of people. Everyone works in lots of different areas. We've now got a really big growing photocatalysis division in the group. And the title of my project is Small Molecule Reactions Using Earth-Abundant Copper-1 Photoredox Catalysts, which is such a mouthful that I figured if I put that as the title of my talk, everyone would run a mile. So photocatalysis in general is what I'll talk about today. So you'll see I'm co-supervised with the University of Edinburgh, and you might wonder why I'm working there at the moment rather than just popping back and forth. Few events have happened in recent months and years. Most notably, there's that big thing that's happening at the moment. I don't know if anyone's noticed. And also around about this time last year, my laboratory burned down, which was a bit of a downer. If you look at the brightest window here where there's like some orange flames, then that's where my lab used to be, which is a bit sad. What do these two events have in common, apart from making my PhD thesis quite difficult to write? They do both involve N95 respirator masks. We had quite a lot in the lab because we had to use them and wear them in order to recover all of our stuff from the burned out building. But hey, here's a picture of me rescuing my office plant, which miraculously survived the building burning down. So if you guys ever want office plant recommendations, spider plants, they will live through absolutely anything. But moving on from the slightly depressing current events to much cooler science stuff, I'm going to talk about some photocatalysis. So what is a catalyst for a start? Many of you might drive cars, and if you drive a car, then by law it has to have something in it called a catalytic converter. And a catalytic converter is basically a solid surface that your car exhaust has to be passed over in order to remove and transform some of the more toxic and nasty for the planet gases that your car exhaust contains, and transform them into ones that are slightly less toxic and slightly less bad for the environment. So a catalyst is basically a substance that increases the rate of a chemical reaction without itself undergoing any permanent chemical change. So it just sits there and it helps other chemicals do their thing. But how does this work? Well, if we look at this plot of energy versus time, we can see here we've got some reagents, which for the purposes of this talk, I'm referring to all molecules as being like Lego bricks, because that's how I explain it to all of the schools I go and do outreach activities in. I get them to build models of things out of Lego, and then I can call them chemicals, because they do behave in quite similar ways. If you've got a Lego brick, you can stick them together in many different combinations, almost endless combinations, in fact. You need a little bit of energy to push them together, and you also need a little bit of energy to pull them apart. So we've got our Lego brick reagents over here, which have a higher energy, and then our product Lego bricks that are stuck together, which have a lower energy. But it's not as simple as just taking a path from A to B. You have to overcome an energy barrier, which is this blue line. So this blue line is known as the uncatalyzed activation energy. So this is how much energy you have to put into this reaction in order to overcome this big hill, roll down the other side, and get to your products. Now, normally when you're doing a chemical reaction, you can kind of think of it a bit like cooking. Usually you have to put in some kind of energy, and it's a bit like, you know, you're boiling some water, you have to heat it up perhaps to give it that energy that it needs. But sometimes that's not quite enough, or sometimes you have to boil it for a really long time and it's very time consuming. So what we really want to do is reduce that activation energy, particularly if you're looking at industrial applications. So if you're working with, instead of working with a few grams of these reagents, you're actually working with like 13 tons of the reagents, and suddenly you have to heat up 13 tons of the reagent to 500 degrees for 9 days. That's when things start to get complicated, and that's when people need some catalysts. So what a catalyst does is it reduces this activation energy barrier. And this means that we can do the reaction using less energy, sometimes with sort of no heat input and sometimes with slightly less. So this is really great, and it's been used very widely in industrial applications. Many different things in your life you wouldn't know have touched a catalyst, things like plastics, oil, all that stuff has touched a catalyst at some point in its life. So it's a really cool process, and an even cooler process is photocatalysis, which is what my PhD is all about. So photocatalysis is the catalysis of chemical reactions, which is accelerated by energy or electron transfer, usually driven by the energy of visible light. You can use ultraviolet light, but I won't talk about that today because it's complicated. So a rough diagram of how this works would be, we've got our sunlight here. We can use LED light as well, actually, and that's just as energy efficient, if not slightly more so than using sunlight. So we can use our visible light, and a photon then falls on the catalyst becomes very excited. It has an excited electron, and this electron has become unpaired because it's excited. And if you remember what I said at the beginning of the talk about unpaired electrons, they don't like being unpaired. They don't like it at all. They don't like it one bit. They either want to find a pair or get less excited pretty damn quick. So we've got this very excited catalyst. It's so excited, it's, you know, it just wants to get rid of this energy. Where does it give the energy? It can give it to our catalytic reaction. So this is how our catalyst gets regenerated, and we can use the catalyst again and again, and hopefully just keep using it for a very long time. In practice, it can be more complicated than that. But this has been proven to work for a number of different processes with various different types of catalysts. So we can use organic molecules, we can use molecules that have metals in them, we can use molecules that are all kinds of different states. One of the applications of photocatalysis is something like water purification. And I took this nice little figure out of this paper in Environmental Science Technology that I read the other day. Just made me feel very related to. Yeah, it's a very relatable chemistry figure because photocatalysis has had a lot of positive hype recently. It's actually been around since the 1960s, 1970s. People have been leaving reactions in the sun and finding out what happens for ages. But there's been a bit of a peak of inflated expectation because everyone goes, oh, photocatalysis, it's this new process and nobody's used it before and we need to develop all these different reactions sort of mostly through trial and error and not quite knowing what we're doing. And then things do start to go wrong and there's some negative hype and everyone goes, oh no, photocatalysis isn't the solution to all of our problems. We need to keep things the way they were before. But I'm here to say that actually, I think we can reach a happy medium here. We can make some progress towards some niche applications of photocatalysis and have some more practical expectations of how we can use it for various different processes. So for example, water purification in developing countries, which the Robertson group in Edinburgh has done quite a lot of work towards, which is really cool. Involves things like turning toxic pollutants into more biodegradable organics, or making them into perhaps compounds that could be filtered out of water solutions more easily. And this is really easily applicable in rural countries and developing countries, that kind of thing. So it's totally doable. And I want you all to suspend your disbelief about photocatalysis, because I'm about to talk about my project, which is very cool. So this is how I tend to introduce my project when I'm doing outreach in schools. I like to introduce climate change, which we're all painfully aware of at this point. Global warming, oh no, says the melting ice cream cone of a planet. So we all know that, you know, we as a species are just producing an awful lot of greenhouse gases, of which carbon dioxide is kind of the big bad, from all of our planes and cars and cows. But carbon dioxide is actually a really simple molecule. It's basically just a carbon with 2 oxygens bonded to it. Why is it such a pain? Why is it so difficult to get rid of? Well, if we have a look at using sunlight to break down CO2, which is kind of problem number 1 in my PhD, we've used photocatalysis for quite a long time, probably about 15 to 20 years now. It's been used certainly in academic labs and in some quite niche industrial applications. It's been used for fine chemical synthesis very successfully, using a wide range of different photocatalysts. But a challenge still remains, in the sense that carbon dioxide, we want to transform it into something that is perhaps not a greenhouse gas and also is more useful. So we could turn it into some kind of fuel. We could turn it into things like formic acid, which can be transformed into fuels. But the issue with carbon dioxide is that despite being so tiny, it has really, really strong bonds. It's actually really difficult to do anything to it because it's very unreactive. It just wants to kind of sit there. So this is where catalysis comes in, because if we're thinking about the energy barriers, we want to try and lower the energy barriers for how much energy it would need to turn carbon dioxide into something more high value. So that's problem number 1 of my PhD. Problem number 2, because I love to make things more difficult for myself, is we want to use something that is not a conventional photocatalyst. So conventional photocatalysts that are based on metals, which is what my PhD is all about, tend to use these 3rd row transition metals in the periodic table, and occasionally 2nd row ones. So they'll use things like iridium, platinum, ruthenium. Iridium and ruthenium are the 2 big favorites, actually. And these metals have really favorable properties. So they're very easy to make metal complexes out of. So that's where you get a metal and you coordinate some kind of organic molecule to it, and it's bound to that metal very strongly. They're very stable. They absorb light really well. They absorb quite a wide range of frequencies of light. And they also have very favorable reusability properties as catalysts. However, there's many downsides to 3rd row transition metals, as any inorganic chemist can tell you. First of all, they're really toxic, which we don't want to be working with. And second of all, if you look at some of the elements that are around them, like platinum and gold, you wouldn't be surprised to hear that they're very rare. So iridium, I think we have approximately 3 tons of iridium on the entire planet. And that's all we have. We don't have any more. You can't mine anymore. There's such tiny quantities of it. It's very, very difficult to obtain. And what do we need iridium for? Well, look at your phone. That's got iridium in it. Every single smartphone on the planet contains iridium, along with lots of other quite niche and very rare elements. But that's a whole other separate monologue for me to go on. So we need iridium for other things. And it's also toxic, expensive, not that great, kind of overhyped, if you ask me. Don't tell my supervisor. So 1st row transition metals are where it's at. They're really cool. We have loads of them. There's millions of tons of copper. In fact, we have millions of tons of copper spare. So it seems like a really good target to be using as a photocatalyst, because we can also make complexes out of it that have really favorable properties. There's been some limited success already in the literature, so we figured this is the way to go. So this is challenge number 2 of my PhD. Inorganic chemists just being like, nope, don't want those 3rd row transition metals, don't care how well they work, we're going to use the 1st row transition metals. So this is my research process, or this is at least my expectation of my research process. When I was but a poor, naive 1st year PhD student, I looked at this and I was like, yeah, this seems reasonable. So one nice thing I really like about my PhD is that it has a really synergistic approach to the research that I'm doing. So I start out looking at literature work. I'll then model whichever complexes I want to make using computer modeling. So we submit code to a supercomputer on our university campus, and it models the complexes for us. It tells us what sort of structures to expect of the complexes and what their properties are going to be. Then I'll do the stuff that's my absolute favorite part of my PhD, which is the synthesis of the catalysts, where I get to do all the stereotypical chemist things, going into the lab, bubbling flasks, rainbow things, really cool. Then I have to do the much more time-consuming part of actually purifying it all, because that takes forever. A synthesis takes about a day or two. The purification could take anything up to a week. Then I get to go into the physics department and test the properties of the catalyst. So for example, I want to test what wavelengths of light they absorb, so what the best wavelength of light to excite them at would be. So for example, the catalyst might absorb blue light really well, so we use specifically a blue lamp in order to do the catalysis. We can also do things like passing an electric current through the catalyst and seeing how it behaves when we do that. And this is all really important. We can cross-reference it back to the literature and then use that as a building block for testing our catalysts. And this is something I've had great success with, which has been really exciting. And then once we've optimized the conditions of the testing, so we can sort of really work out what makes the catalysis tick, how it works, what the mechanism is, and then what we could potentially be using it for, we then get to our useful outcomes, which could be things like academic research papers, the possibility of using this for applying it to fine chemical synthesis, making things like pharmaceuticals. So it's all very exciting. However, this is the reality of my PhD. Things don't always go to plan. My computer models don't always behave themselves. Most of the time they do, but sometimes they don't. The synthesis can be quite complex, and the useful outcomes can sometimes seem very far away. But overall, it's been a pretty cool journey, and I like the fact that I've been able to be involved in every step of the process, which is really cool. Having said that, I will not be showing any of my results of my PhD, despite having worked on them for 4 years, because literally the week that the lockdown happened was the week I was going to be gathering my final results to fill in all the gaps of the paper that I'm writing about this, and obviously haven't been allowed in the lab. So for intellectual property purposes, I will be continuing to use Lego bricks to represent all of my molecules, and watch this space, or watch my Twitter account for when it does finally get published. That said, look at these cool photoreactors. These are the photoreactors that we work with in our group. So the batch photocatalysis reactor here, which is our Mark 1. Actually, we had a Mark 0. My supervisor, Eli, I think one of our first few meetings or so, we were chatting about photocatalysis. And he said, oh yeah, we've been looking at sort of building new photocatalysis reactors because lots of this research is so early days that we're still looking at sort of building our own reactors and we're optimizing what's best. He gave me this collection of Lego bricks and was like, maybe you could try doing this, because there was a guy who's been working in the group who's been trying to build a reactor out of Lego bricks. And I was like, okay, cool. Unfortunately, the Lego bricks did fall apart. However, one of my colleagues, Shenfei, did some great work building this batch photocatalysis reactor here, which has basically a big dish, and you wrap around a load of LEDs around the inside of it, and this can irradiate whichever samples you put inside. You can stir it from the bottom with a magnet, and then we can cool it from the top using a fan, because believe it or not, LEDs actually get quite hot. So this is really cool, and this gave us some nice results. And then I also got the opportunity to work with a flow photocatalysis reactor. I was lucky enough to go on a research placement to Montreal to work in the lab of Professor Sean Collins, who does a lot of work on flow photocatalysis. They're a really great group, and they built this photocatalysis reactor. And this has a huge advantage over batch photocatalysis reactors, because a batch reactor has a really small surface area inside the reaction vessel. So you're not going to get very good irradiation, particularly if the product becomes quite dark in color, because that means the light can't penetrate it very well. So you end up with the reaction just kind of plateaus out. But if we have a flow photocatalysis reactor, we have this huge surface area of transparent plastic tubing that our reaction is running through for quite a long time. And this means it's exposed in a much larger surface area to the light that we're irradiating it with. So this gives us a much greater reaction efficiency. Often the reactions run much faster, and they're also a lot more sort of generally easier to run than a batch photocatalysis reactor that involves a lot of sort of workup steps afterwards. So that was extremely cool. Recently, we've constructed these Mark II photocatalysis reactors. So with some of the guys in the engineering and physics department in St Andrews constructed this mirror box design, which basically we have underneath all of our reaction vessels, we have just a plain black box, and inside it's coated entirely with mirrors. On the top of this reaction vessel, we can also slot in a lamp which irradiates from the top. All of the radiation is then sort of bounced around the inside of the box by the mirrors, and this means that all of our reaction vessels, the little tiny vials here, are irradiated evenly from all around, which is really cool, and it also looks awesome. And another really neat thing about this is we've got some fans on either side. We can also fan cool it from the top if we need to. We can replace the lamps with different frequencies of lamp, which before was quite a time-consuming process. You'd have to reinstall them into every single dish, but now you can just slot in, slot out, and we can have sort of everything from purple all the way up to white LEDs in various different colors to irradiate different reactions. We have 3D printed removable reaction vial holders, and we can fit anything between 8 and 16 reactions, I think, depending on the vial size. This has massively improved my working efficiency, because before, when I was doing reactions, it was one reaction would take me maybe 2 or 3 days, so I could get 8 reactions done in about a month. Now it's a case of I can do 8 reactions in 3 days, which is really cool. So we're really hoping we've got a bright future, pardon the pun, with these photocatalysis reactors. So the story so far with my PhD is I've designed these copper complexes with which we can think of kind of as a molecular antennae. That's how I like to describe them. Essentially, the ligands that I've designed, which are sort of specialized, quite complex organic molecules, will absorb the photon from sunlight. This will then excite our copper center, which becomes very, very excited. In fact, so excited it starts to glow. Here's some cool pictures of that. And it can then give its energy to our photocatalytic reaction and give us a wide range of different products. So this has been really successful for about 4 or 5 different reactions. We've had really nice results of various kinds of products that we can do, various different kinds of reaction mechanisms, transferring both energy or electrons, which are 2 quite separate reaction mechanisms. So we're really excited we've managed to do both of those. In terms of transforming carbon dioxide into more useful byproducts, this is quite the challenge, and this is sort of the next step of the challenge, in the sense that we need to go back and alter the structures of some of our copper complexes in order to provide higher levels of energy to our carbon dioxide. So this is like a future challenge for us. But some conclusions and future work for us is, what can we really use my photocatalysts for? So we have here some sort of simple building block molecules that we're going to funnel into something more useful. They're very simple building blocks, but actually they're very valuable. So if we look at this one here on the far left, this has got an alkane, which is a triple carbon-carbon bond. This is really synthetically useful if we're looking at things like drug molecules. This kind of molecule here would be really difficult to make in a pharmaceutical company. This would take 5 or 6 steps of synthesis with some really toxic reagents. Similarly, we also have this pyrrole group and various halogenated compounds that would be really useful in various different fine chemical synthesis. So we're using a green energy source that's cheap to run, really quite quick. We're saving a lot of the sort of steps, and therefore saving a lot of money, and can apply it to fine chemicals and pharmaceuticals. So it's all looking really cool. And it only remains for me to thank the many, many people who, I really hope I haven't forgotten anyone's names from here, who have been involved in this research over the years. So first of all, massive thank you to the EZC group, my original St Andrews fam, who I miss them all very much. I wanted to put in 2 pictures, so I've got a picture of me with the group and then the group without me, which is very sad. The Robertson group, who have been really welcoming to me in the last 6 months since I moved to Edinburgh post-fire. And also everyone in the Collins group, who amazingly managed to teach me all about photocatalysis while also operating mostly in French, and I don't speak much French. So big thanks to them, all of the technical staff and everyone who gave me money, and also the Scottish Fire and Rescue Service, who have been pretty good recently. And finally, thank you all for listening, and I hope I can answer any questions.